One of the big things that you'll learn in terms of like interviewing and stuff is going to be what is known as like this big O. Do you guys, you want the light on or off? Oh no, you don't. I mean, do you guys want it on? Is it? Hit it off and we'll see. We'll make a choice. Okay, leave it on. Okay, wow. Apparently they want it on. Sure, leave it on.
There's no like happening.
I would love that. I've requested such, and they said no. Oh my goodness! Wow, what powerful use of technology. No, they said no. Yeah, just leave them on. The screen. The screen's pretty bright. Is that okay? Yeah, you gotta leave it off. I'm sorry. It's fine now. I could just lecture to a group of like blank faces, you know. All right. So the idea is, at some point you will have to understand what Big O is. You'll probably be asked some questions in terms of like interviews, what your whiteboarding interview is going to look like, and so kind of going to define what some of these terms are. This is a very, very basic introduction so that you can speak a little bit more intelligently and you can feel confident in what you're saying. And so you understand the underlying concepts behind it. So you haven't probably seen this in a while, the old SWOBOT. So students will be able to, in case you forgot that acronym, we should be able to at least define what an algorithm is. We'll talk about some of the big O terminology so that it's less intimidating. And then you can identify code that runs linearly, logarithmically, quadratically, or finally, there's something I should probably update. This is like constant time. We'll talk about what those are. And then really kind of like this last thing that's really important is like understanding the time and space trade-offs and how you can leverage all that in like interview questions. So let's begin. Before this, you probably should have received, which I did not send to you guys because I knew that you were working on projects and some of you had code challenges, so very likely you probably weren't going to do it. So we're just going to discuss this as sort of like a learning point. So the idea here is you basically need to write a function that is called hasTargetSum. It receives two arguments, an array of integers and a target integer. The function should return all pairs of numbers found in the array that add to the target number. Now, this is very, very common in terms of what you will see, what the deliverables are, and what exactly is explained to you. It should be, what is the problem set, right? What do you have to build? What is the input? What is the output? And then ultimately, some examples of input and output. So you can kind of try your best to understand. It's very tricky when you're on a whiteboard if you don't actually understand what the problem is asking for, and you should immediately start to ask questions. Right, like, hey, I'm not sure what that really means. Can you give me some more examples? And it's like very fair, right? So don't try solving a problem unless you understand what it's actually asking you to do. So here, the function hasTargetSum, when run, takes in an array of integers and a target integer. So in this array of integers, I'm basically looking for, all right, all the pairs of numbers that add to the target number. So for example, right, like -1 and 3 add up to what? 2. Oh, okay, oh, very good, yes. Oh, it's probably an easy question, right? So what is 3 plus 8? 11, great. So the idea here is at some point, 1, 2, 3, 4, or no pairs of these numbers should add up to the target number. So the idea is that if your function runs correctly, you should get -1 and 11, because that obviously returns 10, as well as 3 and 7, those return 10. Some important questions to ask are duplicates okay? And are the arrays 3 and 7 and 7 and 3 considered different arrays? Right? Because the idea is that you can have those combinations. And so those are questions that you should be asking in terms of like when you're in this interview. So for right now, if you return repeats or you return 3 and 7 and 7 and 3, it's totally fine. Sometimes they'll give you these false constraints where they'll say no repeats, no duplicates, and that becomes a little bit more challenging. All right? Any questions so far in terms of like what to kind of expect in terms of what these questions would be looking like in terms of like these whiteboard algorithm questions? All right, you can get a ton of practice. There are like dozens of websites that do this for free, so you should probably get into the hang of doing all these things, but what we'll talk about today is how to explain how fast and efficient your solution is, right? So, defining Big O, right? So, Big O is a very intuitive concept. And really what it is the bottom line is a way to compare algorithms to each other. How can I tell whether or not my solution is either faster or slower than yours in terms of like its runtime? And so that's like a really weird thing to say. But the idea here is really, let's start by actually asking this question. Like, what is an algorithm? Okay. Anakin? Yeah.
An algorithm is a set of instructions.
That's exactly correct. What's up, man? Oh no, I'm Gucci, man. I have hands.
Okay. It should have been in here earlier.
Oh, my hero. Does this even work though?
It's just press
Oh!
That's what it is.
Sometimes the laser pointer gets like stuck in the projector and then like it'll go red and then like disappear. But
Yeah.
this is next level lecturing over here. No, I'm cool. Powerful. All right, it's absolutely that. It's just a set of instructions, right? So like an algorithm for making coffee would be what?
Like coffee grounds and filter, put the filter in the thing.
Right, wake up, right? Roll out of bed, walk to the kitchen, or whatever it is, right? So like, what is the step by step? But yeah, you're absolutely correct, right? Just like how to actually make the coffee. So let's actually define like Big O. So the idea here is an algorithm is just a procedure or a set of instructions. So here's some very easy ones that you've probably seen before, right? Lather, rinse, and repeat. Unfortunately, this one is a bit of an infinite loop, which is kind of tricky because if you lather, then you rinse and you repeat, guess what you're doing again? You're lathering, rinsing, and repeating. So this is what it would look like in theory if you were to try to translate some of this into like code, right? So while your hair is not clean, you lather and rinse. It's just pretty funny, right? Ha 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 ha. Very good. My God. So another example is like, what about like cooking or recipes, right? So first thing is like preheat the oven, microwave the butter for 40 seconds, unless you have it at room temp, and then blah, 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 bake for 7 to 10 minutes, and then eat, right? Well, let cool for 5, otherwise the roof of your mouth will hate you, and then like consume and enjoy, right? So cool. Look at this. Ooh. All right, so now that we kind of understand this algorithm, all right, let's talk a little bit more about the different ways we can evaluate how an algorithm is defined. So the first thing about Big O is we talk about this like time. The way we measure time in Big O is the absolute worst case scenario. So for example, let's just say we're trying to look at how this dot find works under the hood. You have an array of 1 to 10, and you run dot find. All right, it takes in this n block, and if n is equal to 3, right, return it. You like that no return statement? Ruby was so nice to you. Ruby was so nice. Right, and look at these exact set of instructions in terms of how this whole code works, right? So the first element is 1. All right, and if that's yielded to the block. The block is this right here, the doing n. So now n is 1. That's the first element. Did it meet the condition? Sorry, did it meet the condition? Is 1 equal to 3? So n is now 1, and then it interpolates it here, and is 1 equal to 3, true or false? Right, false. And so then it runs back into the iterator, right? And now n is 2. Is 2 equal to 3? No, and then it starts over again. And now 3 is yielded to the block, right? 3 is now n. Is 3 equal to 3? Yes. So doesn't make sense to measure how fast or efficient an algorithm is based on the best case scenario. Because what if we were looking for 1? It should find it. What if n double equals to 1? In theory, it'll find it on its first hit. But what if we were looking for 10? It'll find it on the last hit. But what if we were looking for 11? It will essentially go through every single thing in the array and then be like, oh, just kidding, it's not even there, dude. So the best way to measure is what is the worst case scenario, right? What if you have to do every single thing to get to the last point? How fast does that run? And so Big O essentially is like measuring how fast something runs in the worst case scenario. So far, so good? All right, great. Blah, blah, blah. This is a very important graph we'll be referencing, but the idea here is this. Looking at all of these, it should kind of be like, oh my goodness, math, and you should maybe get scared. Don't be scared. I was on the math team. Math's not that bad. The idea here is let's actually think through which one of these 4 options is this dot find. Well, let's think through. Ready? If I were to do dot find and I had 10 numbers, what is the absolute worst case scenario in terms of how many numbers the dot find has to go through? 10. But what if it was 100? How many numbers would it have to go through? What's the worst case scenario? So it seems like the worst case scenario is in a 1-to-1 direct relationship with how big the array is. Does that make sense? Right? The larger my array, the more numbers I have to go through to even kind of run through. So every single time you're doing an iterator, any iterator would have a sort of speed efficiency of how big the array is. It's completely based on how many numbers are in the array. So in this dot find, right, n right here is going to be 1, 2, 3, 4, 5, 6, 7, 8, all the way until it's 10. So we can think of n as sort of how many numbers are in the array. So in terms of any iterator, how fast time-wise would you say it takes to go through an array knowing that n represents the length of the array? How fast would you describe the speed of an iterator if n is the number of items in the array and we're measuring it based on the worst case scenario?
The length of the array.
Right, which is n, right? The length of the array, which is n. So an iterator would have a speed of what is known as just n. So if I was talking about big O, and I said the big O of a find, a big O of dot each, the big O of map is big O of n because it matters how many things are in the array. And that's kind of like this first introduction to like when someone says like O of n, so big O of n, it just means that I have to go through every single thing. So far, so good? If I have to go through every single thing, the idea here is the number of items in the array, and then t is time, right? So this is no items, right? 0 seconds, right? That's like infinite seconds, and that is number of items in the array. Of all of these things, think about it, right? You have a 1-for-1 correlation. If the number of items in my array goes to 10, it should take me 10 seconds, right? So if I go 10 and 10, it puts me here. If my number of items in my array is 50, that would take me 50, quote unquote, seconds. So it grows exactly in a 1-for-1, and that would put me 50 here and 50 here. It puts me here. But if my items were at 100, I would have 100 items here, and that would take me 100 sort of, not really seconds, but like 100 units of time, so to speak. And that puts me, if this is 100, and then this is 100 here. So you have a direct 1-for-1 correlation, right? Which one of these lines would it be?
Linear.
It should be linear, right? And that makes sense. That means that as my array grows, the amount of time it takes to process grows in exactly that same size. So far, so good? So if you were to say that an iterator, enumerable, like dot each, dot find, a map, reduce, any of those, you say is O of n, or is linear time, would that make more sense to you? Who would feel comfortable saying that? Like, hey, listen, I'm just going through every single item, and that has a big O of n, right? So an iterator has a linear time. That being said, any iterator would be the same. So if I did a for loop for an array of 100 items, which one of these would that be? Linear. It has to go through every single one, right? So far, so good? All right, cool. I mean, like, big O's really not too crazy, right? Like, you're starting to feel pretty good about this? Yeah. All right, so let's do this now. Ready? Let's talk about, like, something that's a little bit more functional, so to speak, right? I have this average function. And this average function just takes in an array, naturally. And then I run dot reduce on it. Reduce, obviously, will take in a starting point, so you're just going to start at 0. And then what it's going to do is just going to add up all the numbers. It's going to accumulate all of them. And then it's going to divide it by the size of the array 2f, because we like to be very precise here. So just 2 float, in case you forgot what that is. A lot of students are always like, oh man, I forgot Ruby. I'm like, it was like a month ago. It's wild how fast this program goes. So I have another method called contains average, and that takes in an array. So if my average is equal to the average method being run on the array, I simply check to see, does it include, right, is the average inside the array? So far, so good? Nothing wild, right? Yeah.
Why is the float on the rear on size? Wouldn't it be a thing? Or what?
I mean, you can just, this is sort of like irrelevant. Huh? No, it's irrelevant. I mean, if I wrap this whole thing in parentheses and put 2f, that'd be cool too.
I was just wondering.
Yeah? Awesome. So, if I have a, right, and I put average, and I put a, what should it do? It's going to run average, and then it's going to run this reduce. It's going to go through every single thing. It's going to add them all up, and then it's going to divide it. So, 2 plus 3 plus 4 plus 5 plus 6, and then divide by 5 should be what? I mean, we could easily just kind of take a look, right? Like, what's like the middle number there? All right, for those that are bad at math, you could just steal 2 from 6 and add it here, and that puts it at 4. You could steal 1 from 5 and add it to 3, that puts it at 4. So you'll have 4, 4, 4, 4, 4. Cool. I used to be on the math team, just like little tricks that you pick up. But either way, you can't really do that here, you know, because you have like a freaking 100 right there. But the idea here is, if I want to run this, right, dot includes, and check it after it's run through the average function, what would you describe the big O of this method? If I wanted to find whether or not the average is actually inside the array that I gave you, because that's what it's asking for, right? First you have to find the average, and then you have to be like, hey, is that average even in the array already? So obviously with A it's true, and with B it's false. That 100 really just messing up the curve there. So how long do you think this will take to run? What's the big O of this? Well, it's kind of hard because you don't really know how to calculate it, but let's try calculating it together. The idea here is we have, what is reduce?
Total zero, thing that you want total for.
Well, what's the big O of reduce?
Isn't it? Is that a lay dot include question mark? Then
What?
you just put in parentheses whatever you want.
Array dot include.
It's not like a question mark, and then you can just put in average, and that would be, doesn't have like the grade through it. You just check it inside the array.
Not exactly, but let's do this. As it's written right now, right, let's calculate the big O. The idea is that reduce is one of those enumerables. It goes through every single thing, right, and it adds it all up. And then it does one additional unit of work. So reduce is an enumerable, and it's just big O. And then it does this divide. So that's like one extra thing it has to do. So we can think of this whole method, which like the first 5 lines are comments, right? So whatever. This whole method right here is O plus 1. You have like the whole iterator, which we've discussed as like O of n, plus this one divide. Like it has to do one additional unit of work. So far, so good. Okay, great. Now, what about this dot includes?
Going through each one. No?
It's going through each one. So it's really, if you think about it, right, mathematically speaking, you have O of n plus 1, right, which looks like this. If you ever want to see it written, it's O of n plus 1. And then you have, again, this dot includes, which is going to be O. So if you're really savvy, the idea is that if you added O of n plus 1 to O of n, you should come up with something like O of 2n plus 1, because there's two n's there, and then you're just adding the 1 to it. All right, so far so good? Okay. All right, boop. Unfortunately, that's not actually what the big O is. If you got to this point, congratulations, right? That's exactly the idea behind it. However, this is not the actual answer. Does anyone know why?
Because you only care about the worst case scenario, you don't care about the constant.
Yes, we care about the absolute worst case scenario. So we want to drop what are known as the constants. The constants there are 2n, well 2 rather, times n, and the plus 1. So here's the idea. Before I actually kind of get to it, I'd rather just explain it because it makes a little more sense. Plus you can look at the dogs. The idea here is if n is like an array of 7, the 2 coefficient is going to be what? How important is it? Right? Like when you think about processing time and that your computer can calculate millions of things at once, right? If the array is 7, you're looking at 7 times 2, which is 14, plus 1. If I have a million, right? What's 2 times a million? It's 2 million. Plus 1, you're really getting 2,000,001. If I have 20 million, right? Times 2 plus 1 is 40,000,001. So the idea is that the plus 1 is not actually affecting the speed of your algorithm at all. If you can run 100 miles an hour, and I told you you needed to run 1 mile, or you need to run 1 inch, is that 1 inch going to make a difference if you're running at 100 miles an hour? Like, not at all. Like, you're running so fast, like that 1 inch is not going to make a difference whatsoever. So that plus 1 does basically nothing for you in terms of like calculating how fast it's running. All right? The idea is that now in the world, we're dealing with, I don't even know what this number is, so I'm just going to make it up, but like zillions of bytes of data. Because think about like just memory in general. How many users are on Facebook right now? I think it's like 3 billion. It's like almost half the population. Well, like a third of the population. It's almost at like 9 billion, right? So just that in and of itself, right? There's 3 billion objects just in users. How many posts do you think each person makes? On top of ads, and on top of comments on each post, on top of the fact that every time I click like, it creates a like object. So how many likes, comments, and posts for 3 billion users do you think are objects in memory in your database? Yeah, like zillion. Let's just use zillion for fun, right? Oh yeah, oof, whoa, whoa. The idea is that just multiplying it by 2, that's not going to change it like crazy. It's the amount of objects in the array that's going to change it. So the coefficient of 2, while can have an impact, is not going to be the biggest impact. So the worst case scenario is going to be what is the actual biggest impact to how fast your algorithm runs. Plus the coefficients are always constant. If I'm comparing one algorithm to the other and I'm just multiplying by 2, that's not really sort of going to make or break the algorithm. It's how big the main end component's going to be. So far so good? So this should actually still break down to O of n. All right? So if you're calculating big O, this whole thing should still be O of n. Who feels like all right with that? Yes, no? Check or hold?
Question on why, I understand the plus 1.
Okay.
Why 2n? Isn't that the worst case scenario? 2n?
Yeah, but it's not going to impact it that much as like your scale grows. So n is going to be the worst case scenario. What is the biggest thing impacting the speed of your algorithm? Yeah. Okay. So, all right, cool. How we feel about like linear time, like big O of n, just O of n linear time. Good to go? All right, the next thing we're talking about is logarithmic time. So, imagine the world's worst dictionary, right? You have a dictionary, and for whatever reason, Funkmaster Flex, DJ Khaled got together and decided to throw a little remix on there, and none of the words in the dictionary are alphabetized. It's just you open it up, you could get B, you can get K, you can get F, you can get G. It doesn't really matter. It's just in any random order. Okay? How would you go about finding a specific word in that dictionary?
Page by page.
Page by page, right? That's terrible. So you have to essentially just look for the first word. Is it what we're looking for? Nah. Okay, great. Goes to the next word. Until you hit the end of the dictionary. That's terrible. Even the word like add, theoretically, in this terrible dictionary, could be on the last page. Theoretically.
Are we saying in a case where you're trying to find a word specifically, or find the word? Or
Find the word in the dictionary.
So why would that be different than like just doing an include checking it's in that dictionary?
I'm talking about like real life. If you were physically looking at a... Okay, fine. Okay, fine. So, clearly, right, if I'm looking for a word in the dictionary with 10 words, it would take so much less than looking in this terrible dictionary with 10,000 words. So far, so good, right? But we have an alphabetized dictionary in real life. So the idea is, if I'm looking for a word with the letter C, what can I do realistically?
Turn to the C section of the dictionary.
I could just turn to the C section of the dictionary and essentially eliminate everything D and on, right? And then if I'm smart about it, I can even cut out like B. And so I'm just looking at like the 40 pages of C in this dictionary. So if you're thinking about that, am I really sort of like going through every single word if my dictionary is sorted? No, it significantly cuts it by a lot. But by how much? Is it exactly 50%? No. How much percentage would you say you've cut that out?
25 out of 26.
But are there exactly the same amount of words per letter? No. So it's hard to say, but you know you've cut it a certain percentage, but you can't say specifically what that percentage is. So the idea is this, right? Boop, boop, boop. Okay. If you open the dictionary to exactly half, all you would have to check is it in the first half of the dictionary or the second half, right? And then you cut it in half again and look if it's in the first half or the second half. So each time you're essentially cutting it in half, right? If you were to do it like systematically. If I'm looking for something in G, I can go right to half of the dictionary and go, you know what? I don't even care about the second half because G's toward the first half. So I can cut out that part. And then I cut it in half again and go, wait, is G on this half or on this half? And I remove half again. And I can keep going that way. So I can systematically remove what is not there for sure and then change what I'm actually going through. So, boop, boop, boop. Let's talk about something, but just keeping that in mind, right? I have a linear search function. And so now I'm jumping between Ruby and JavaScript to like, not to trick you, but to make you work. So this idea is like, I can't believe Alex did this. There's actually an array of like 1,000 unsorted numbers here. If I like were to copy and paste this all the way, this guy's a monster. But check it out, ready? In the linear search below, basically what I'm doing is I'm taking in an array, so like of 1,000 unsorted numbers, and I'm looking for a very particular number. I'm going to go through every single number, and I'm going to log, hey, this is how many I have left to look at. And then I'm going to essentially check to see, is the element I'm on what I'm looking for? Cool? If it is, give me the target. Otherwise, it's no good. Keep going. Cool? So if I were to actually take this function, and I would just go into any sort of browser, because the browser just runs JavaScript, right? Powerful. With that, and I would take, oh my goodness, array. Oof, wow. Oh no. Oh my goodness. Oh, does it not let me do it? Hold on. I think the array is actually in here. I think in the preview it like cut it out. Oh my god. Oh no. Huh. It's all right. Let's do this. Let's actually make an array. Const cool array is equal to an unsorted array of, I don't know, 4, 5, 7, 6, 2, 1, 8, 9, 10. Am I getting all of them? That's good enough, right? Good enough. Great. Let me run this function now and see what happens. Oops. Linear search, and it takes in an array and a target number. So what number would you like to look for? 2? Sure. So it goes through, it searches, right? Every single time it goes through and eliminates 1 from the array. And it goes through. So far, so good. All right, right. Let's go back to this. Look at that README preview, right? The idea here is, in theory, if I were to look for 55 inside this array of 1,000, this is kind of what it would give me if I actually put in an array of 1,000, which is insane. It would give me all the way until I hit 55. Whew. But what if we had a sorted array and I ran it through that same exact function? Would it make it any faster?
No.
Why no?
It just starts at the beginning and goes to the end.
It just starts at the beginning and goes to the end. It doesn't really matter if it's sorted or not. So this algorithm is fairly inefficient. It's what speed? Linear is O of n. It doesn't matter what the inputs are. It's just going to go through every single one. There's a 1-for-1 ratio of how fast it's going to work. Now, taking in mind what we talked about earlier, right? Linear search, regardless of whether we run it with the unsorted array or a sorted array, it's just going to be linear time because of that for loop that's in there. But if we do have a sorted array, and Alex loves this, like we can do better. Right? He ghetto claps in his readmes, and I love it. Below is the binary search, right? And this is kind of what we talked about in terms of that dictionary, and that is it's still going to console log how many are left, but what it's going to do, and just mind you, I believe this function is, yes, this is a recursive function. If you haven't got to recursion yet, don't worry. I may or may not give you a lecture on recursion when you get to Mod 4, but that's not really important right now. So the idea here is you do midpoint, right, and you run math.floor. You take in the array length and you divide it by 2. Why would you want to do that? You want to split it, right? And now you have like a middle, which is the array at the index of the midpoint. So if I have 1,000 things, I take the length by 2, I get 500. So if I take the array at index 500, that's plus minus like the half, right? So what I'm trying to do is I have the array length. If it's greater than or equal to, I'm sorry, less than or equal to 1, I'm going to return the middle if, all right, the target, have you seen ternary arrays yet? It's just like a fancy conditional, meaning is the target, otherwise it's false, right? Is the middle the target? This is the condition. Is the middle the target? If it is, return the target, otherwise false. That's all this is saying. So far, so you with me? All right. Now, if the middle is the target, return the target, we found the thing. Else if, right, if the middle, right, let's just say the number 7, and I'm looking through an array of 1,000 and it's sorted. So if 7 is sort of like greater than or equal to the target, then you're going to look in that half. Otherwise, you're going to look in the second half. Else if the second half. And then it's going to run it again. So what that means is if it's in the first half, cut out the rest, run this function again, which is going to cut it in half and look for it again. Cut it in half and look for it again. So that's like the recursion part. But the idea here is if I put in a sorted array and I looked at 200, look at how fast it runs. There's 1,000 things I need to look through. I check to see if it's the top half or bottom half. Right? Then I cut it in half and I only look at the 500. Then I look at the 250. Then I look at 125, 63, 32, 16. Until I get to 1, I see you. So it's always cutting it in half. So this is running almost, the idea is that It's running faster because it's sorted, because I'm cutting everything in half, because I know it's sorted. So the idea here is, even trying to find something like 201, I only have to do like, what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 before I can get to it. Right? And so it's always almost going to be like 10 sort of operations before I get to the number that I want, because it's always cutting it in half and checking, is it below or above? Is it below or above? Yes, and then I'll get to you.
Why does it matter if it's sorted? You can still check if right is below or above.
Let me ask you this, ready?
I mean, the dictionary more if you're just trying to find C and everything and C is better than sorted like numbers.
Okay. If I split this in half and I'm looking for the number 2, is it in the top half or bottom half?
Or
Right. It's easy to see, right? Wherever, right?
no, I understand.
If I split this in half, can I guarantee that 1 is on the left side?
No. Left side, no.
Like, is it in the left side of the array or the right side of the array? Can I guarantee it mathematically?
No.
No.
But
So it needs to be sorted.
aren't you just checking if the target is in one of the sides? Or you're checking when it's on the left side?
I'm checking to see what side it should be on. So the dictionary analogy is exactly the same. And that is, if I'm looking for B and I split the dictionary in half, is it on the left or the right side? Is it in the earlier or the later half of the alphabet?
But now we could say that it's on the right. If we split it in half, it's safe on the right.
Mathematically speaking, can you calculate with an unsorted array if 4 is going to be above or below the middle number?
Okay.
Okay, fine.
A lot of discussion now. It's long.
Okay.
I don't know. If a computer could just cut the right in half. and
Yes.
say, on the right side, is that target inside there? If not, then it's on the left side. Because we already have it.
It's not doing that. It's comparing.
It's actually checking if the number is greater than or less than the minimum.
That is correct.
Oh, okay. Okay, thank you.
And the same question, then again.
Okay, fantastic. So, let's do this. Wow, it only had to do 10 units of work, right? To find the number 2 on the target number. But what if we used 2,000 numbers and not 1,000, right? And we ran with sorted array 2, now it's 2,000 numbers. And I did 537. I'm looking for 537. Look what happens. It goes 2,000, 1,000, 500. All of a sudden, it finds it again with what I can only guess is 11 tries. So it took 1,000 extra numbers to do 1 extra unit of work. If I do 1,000 again, and I have to search for through 3,000, it'll be 3,000, 1,500, 750, right? And then keep going. So there's a certain point where the number has to increase so much before I have to do 1 more calculation. Does that make sense so far? So this right here, right, is what is known as like logarithmic time. Logarithmic meaning that the time it takes is very slow growing. I had to add 1,000 extra numbers into my array before it did 1 extra unit of work. Does that make sense? If I added 2,000 or 2,001 or 2002, do you think it would need 1 more calculation? Probably.
Can I always just double what your total is? That would add an extra unit of work.
Kind of, but not exactly. So, if you really care, right, this is known as like a log base of 2 for those like math geeks out there. This is why it seems like it's kind of doubling every time, but it's not really. So it's because we're cutting in half, cutting in half, cutting in half, that if you double it, that's the next time it will have to increase the amount of work it will have to do. That's why it seems that way. But there's log base 3, log base 4, there's different types. So This is what it means, right? Just nailed it. All right, so it means it's slow growing. If we go back to this chart, what we can see is that in the beginning, all right, it's going to increase, but then very slowly, all right, the higher the number, it's going to take a lot more of that number to up the amount of time it takes for that algorithm to run. All right? So like if I'm running something in half and half and half and half, and I have 2 things, it does 1 unit of work. But then I have 4 things, it has to do 2 units of work. If I have 8 things, it'll do 3 units of work. If I have 16 things, it'll do, like, you see what I'm saying? It takes more work right in the beginning. But once I hit 1,000, it does 1. Then 2,000, it does 1. Then 4,000, it does 1. And that's why it grows kind of fast in the beginning, but then it tapers off significantly because of logarithmic time, based on that log base of 2, splitting that work in half every single time. Who feels pretty good about this logarithmic time? I can't tell if you're doing this. Oh, sorry. Well, I mean, like, this is essentially the same as this, so you're like, hey, you're fonzing it over here. Send it. Will.
Should our goal be, like, if you're working with a huge amount of data, to eventually be writing more logarithmic code or more logarithmic functions that work way better with big groups of data? Like, is that like a, I don't know, is that something?
It is important for your code to run as fast as humanly possible in most cases. And we'll talk about, like, when you wouldn't. Cool? All right, great. So we went through linear, we went through logarithmic. Now let's talk about this this third one. Boop, boop, boop. Wow. I feel like Owen Wilson. Wow. All right. So now let's think, right? There's this last one. And this is kind of like the task that you were asked to do, quote unquote, right? And that is like, let's build this target sum. So you have an array of integers and a target integer. Do you remember this from the beginning? So the idea here is easily you can make an empty array of results, right? You can look at each element, and then you can try to combine it with every other element. So you go through the first one, and then you have to go through the rest of the array and add it to that first one to see if it equals to the target. So the idea is that, like, if I and j, are you familiar with I and j? When you do nested for loops, right? The first for loop is I, the next for loop you're using j as a variable, that's all. So if I and j equal the target, then you're good to go. That's one of the pairs that should work for this solution. So if you really want to see it, this is what it looks like, right? You have a has target sum, takes in 2 arguments. You make an empty array so you could push into it, right? Because you're going to collect all these array pairs. You're going to loop through the entire array, and right now, array at index I, which is 0, is the current item you're looking at. You're going to loop through inside this for loop, right? You're going to look again at a new variable called j. So the idea here is when you're looking at the first item in the array, while you're looking at the first item, you have to look at every other item. And then when you're on the second item, you have to look at every other item. And when you're at the third item, you have to look at every other item in the array to see if they add up to the sum. And then if it does, then you're going to push it, right? And you're going to push the array of the current and the next. So that's like whatever I gives you and whatever j gives you. And then you can just simply return the results. So let's think through what the big O of this is. I have to go through a for loop. And then in that for loop, I need to go through the array again. It's the same array I'm going through. If I'm nesting through the same array twice, what is happening here? Well, right. Obviously, right? Thank you, readme, plus. But what's actually happening, like, mathematically? It's n times n, right? Like, however many items there are, I have to go through them all again for every single item. So it's really sort of like this, like, n squared you can think of. Like, n times n is n squared. And then that becomes what is known as, like, quadratic. And let's actually break this down. If you have O of n squared, it's quadratic time. And this is extremely fast growing. So if we go back, boop, boop, boop. I've actually put this in multiple places in the README, but for whatever reason, the preview only loads it once. So this chart is like where I want it, but it doesn't want to render. And that's like a markdown preview. So if we look at quadratic, right, it grows very fast. Like the amount of numbers that have to increase doesn't really matter. Every time I add one extra number in the array, it has to go through the entire array again for that one extra number. So if I do one extra number, the amount of work, how fast it's going to run, is going to take a significant, more amount of time. Does that make sense? So that's quadratic time. So let's actually like do that. Boop, boop, boop. Sorry. I know that's not like sexy, but Markdown is not great. So look, big O graph. This is actually the image. It didn't want to load. All right. So now we can optimize, right? We can like refactor this a little bit. And that is, we can put it in one line, like a champ. All right, do you like that? Okay, yeah. Unfortunately, this one-liner doesn't make your code run any faster. It's gonna do the exact same thing. So this is not worth making, all right? Not only is it kind of harder to read, you don't really understand grasp what's happening in like a quick glance, but it doesn't make it any faster. So you're making it not better and harder to read. So minus, right? No bueno. So how can we take this from quadratic time to a linear time solution in terms of like this get target sum? Like that? I feel like I'm just a bunch of GIFs. Like just me. So the idea is that how can we solve this with one loop instead of two nested for loops? That's basically what it is, right? Going from quadratic to linear. And the idea here is, I wouldn't have to go through every single thing in the array if I've already checked it. Right? If I check the first number against the second number, when I'm going through the second number, I don't really need to check every number before that because I've already checked it as a combo. So there should be some way to kind of store the numbers I've already checked and then verify, hey, did I check this already? If I did, skip it. And that way, I only have to go through one time. That make sense? Can we draw it out for you? Or are you guys cool?
You draw it out.
Sure. Boop, boop. You guys like this?
Just I'm a visual person.
Anything for you. So you got boop. You have 2, 3, 4, 5, 6, 7. Those are scary straight. All right. I'm on a touchpad. I'm like proud of myself, you know? So the idea is that right now you're doing this. You're taking this one number and then you're comparing it to the next one and you're going, oh my God, does that work? Does that work? Does that work? Does that work? Blah, blah, blah. And then when you're here, you're doing bloop. And then you're going actually this way to this way, this way, this way, this way, this way, right? And then when you're here, you're comparing again this. So look at all this duplicated work here. And then guess what you're doing here? You're going bloop, bloop, bloop. And then you're going bloop, 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 bloop. Right? Look at all this duplicated work over here. That's inefficient. Right? The idea here is if I'm going, let me just zoom out a little bit. All right, here we go. Oh my God, oh, that was not, all right, I lost it. So the idea is if I check this, I only really need to now go from here and check these. Go here and check these because these were already checked. So I can literally go through one time, and by the time I get to the last item in my first iteration, I've checked every single pair already. So we need a solution to be able to store these numbers we've already checked inside an object, right? Smart. So you could do something like, oh, the nums I've already seen. You could store them in an array, and then you can check to see, hey, is it included, right, in the numbers I've already seen, the number that I want? That's basically like the idea behind it. So far, so good? What's the issue with this?
Isn't that just kind of checking it again?
Includes is an iterator. So includes is an iterator, meaning I have to go through all the items to see if it's the item that I want, which is in fact defeating the purpose because of the way the lookup is and the enumerable and the O of n time on an iterator like includes, right? So when you see things like includes, find, each, right, it sometimes can be tricky to calculate because it's a very hidden iterator. Not like when you see a nested for loop, you're like, oh, I could see that there's 2 iterations. I know immediately it's quadratic. So let's think through. Are there any other data structures that can contain values besides an array? Right, let's talk about hashes for a second. And the last thing called constant time, right? I have a hash. So if I were to simply say to a class and I go, Mendel, raise your hand, what would happen? Okay, obviously with this class, nothing. But if I were to say Aniket, raise your hand. If this class was 40,000 people long, all right, and I said Aniket, raise your hand, how fast is the reaction time for that? Should be instantaneous, right? Or if I were to say like Will, raise your hand, it doesn't really matter how big it is or how many people are here, there's that instant, immediate lookup, right? So in the same way that if I had a hash with the name of Ian, I can simply say, give me hash with the key of name. It'll give me Ian right back immediately, always, right? If I hash as something else, it should return nil because that doesn't actually exist in the hash. So the hash lookup time is extremely fast. It is instantaneous, and it will always take the exact same amount of time. If some process always takes the exact same amount of time, that is known as constant time. So for example, if I were to tell you it doesn't matter what number I give you, how long will it take you to calculate -1? Hello! Right? It should be the exact same amount of time. If I can like, hey, cool, what's 9 minus 1? What's like 40 minus 1? What's like 49 minus 1? Right? It's the same. The calculation is the same amount of time. It doesn't matter what number I give you. How long it takes you to perform that calculation is the same amount of time. So far, so good? Are y'all good over here? Okay, great. Thank you. This class is powerful. All right, so check it out. Ready? Oh my goodness, look at this. Ready? So, all right, think about it like this, right? You have like all these clothes here, right? If I were to look and I pick out a sock, how long will it take me to find the matching sock? Who knows, right? Quadratic time, probably. Good joke. All right, now, if you had a Marie Kondo-like drawer, and I would be like, great, actually, they're all the same color. This is terrible. I can't even say white t-shirt because they're all the same. The idea here is, if this was a hash, these are all keys, right? If I wanted to get a particular shirt, if you knew what shirt you wanted in your mind, and you opened this drawer, how long would it take you to get it? Constant time, right? Because you can see everything, identify and pull it out. It doesn't matter what I wanted you to grab. If I told you what to grab and you knew what it was, then you can grab it immediately. And so that's what the hash lookup time is. It's constant. It's always going to be the same. So if we refactor our code and use an object instead of an array, the idea is simply, if I'm running through this, what I can do is I can do, if I run through it and it doesn't work, right? If I have an array of like 7, 8, 9, 10, and I'm looking for 10, the first thing I get is 7. Is 7 what I'm looking for? No. Then I'm going to do the object at a key of 7, and it's going to point to a value of true. So all I have to do essentially is check, hey, Nums I've already seen. If I pass in 7 again, what's going to happen? I'm sorry, the number I want. It should return nil if it doesn't exist. I'm null, sorry. Oof. It should be null if it doesn't exist. If it's null, we know in JavaScript null is falsy. So then what happens? It keeps going, right? The idea here is like, you can use this object, use the key value, and assign it to a Boolean, and then manipulate that Boolean to kind of keep going. So what I've done is essentially made hasTargetSum go from quadratic time to linear time because now I'm just doing one iteration. If the number came up already, it's going to check in that constant time hash whether or not it was there. I checked it. If I did check it, it's going to go, oh, you looked at it already, go to the next one. Oh, you looked at it already, go to the next one. So I'm doing one iteration. So I'm hitting that O of n, one iteration speed. But what did I have to use in order to get that one iteration? What was the key? Oh my, what happened to my Zoom? Aw, that's sad. That's not even noticeable. Oh. Anyways, what did I need in order to speed up my algorithm? I needed to create a brand new object. So that means that in order to speed up my algorithm, I needed to use more memory. I had to create an object, right? And that object's going to grow, right? Because like as I go through the array, I'm going to push more things into this object, but it means that my algorithm runs faster. So to answer the question right in the beginning, right? In order to make all my algorithms faster, there's a trade-off with memory. And if that's happening, now you have to start considering a bunch of things. So for example, how many different ways can you use the app Netflix? How many different platforms is Netflix available on?
Like browser.
The browser? A native app on your phone? What else? You guys have like a PlayStation 4? Like an Xbox? Okay. What else? Right, Heroku, Fire Stick TV, a Chromecast. Some of these newer TVs have it built into the television itself as an app, right? What is the memory difference between a Apple laptop and a TV? Are they the same? What about a PS3? Old, right? Generations old. Unfortunately, well, fortunately, I have a friend that works at Netflix, and he was building out Netflix for the PS3. Now, the PS3 has a very limited memory allocation for applications. So, he cannot, right, I don't know, I have a lot of Scottish friends. He can't necessarily use more memory, so his algorithm has to be a little bit slower. That's why when you're on Netflix on your phone, Netflix on your laptop, Netflix on your TV, when you turn it on, they operate at slightly different speeds. Like sometimes you'll see it load immediately, and sometimes you're like, oh, it's like that because the TV's a little bit bummy because I bought it in 2010, and the way technology moves, it might as well be a million years old, right? And so there's certain things you have to consider that those functions and methods can't translate one for one every single time. And guess what? Who here has the iPhone 10? Okay, so 3 people, right? Does everyone have the latest and greatest phone? Sorry, we're poor, sorry. Right, I have an older phone and it works, you know? A little slower, but it works, and this is why, right? So now when I deploy an application, the first thing I do is if you look on the App Store and think about it, it's going to check your OS version. It's going to check to see if you have an Android like Pixel, I don't know, 5? I'm not sure. A Google Pixel whatever, or a Moto Droid Z, or an iPhone 10, or an iPhone 6S, like some rich people in the room have. You know what I'm saying? No big deal. I'm just, ooh, wow, powerful. So the idea is that based on my operating system, I understand the level of memory allocated. I have to write my algorithms as best as I can for that platform. So while you always want to optimize, it might not be possible. And you want to optimize to what is possible. Is that fair? And so that's why this is so important in sort of like our industry and why these questions kind of come up. Like, can you understand the trade-off, when and why you might want to, but ultimately the goal is always going to be speed, right? It's 2019. If your app takes more than 4 seconds to load, 1 star, right? And then no one's going to buy your app, even if it's 99 cents. Even those rich people with iPhone 10s won't buy it. It's like a can of soda. Anyways, cool. So, in review, oh my God. We went through a lot today, huh? Great. Who feels good about constant time, right? Logarithmic time, and then linear, and then quadratic. And that's basically the idea behind this first sort of lesson behind Big O. And that's really what it's talking about. So after you get a whiteboard problem like, hey, I want you to find out, I want you to write a function or a method that does has target sum. It takes an array of integers, and then it takes in a target. Please write that algorithm. And then you'll sit there, you'll hang out with the person, and they'll see if they like you, and they'll see how you think. You'll explain your thought process when you're writing the code, and then you'll finish it, and you'll be like, oof, bless up, I'm done, right? You'll even test it. And then they'll ask you, great, what's the big O of it? And then you should be able to somewhat explain, at least using these terms, kind of like what you're doing. Like, great, I'm using 2 loops here. So I'm looping through the same thing nested twice. So this has to be at least quadratic. I could probably get it faster by putting everything in an object. So there's a trade-off there. I think the best I can do is probably like linear time with this sort of algorithm. And then the other person's going to be like, huh. Probably. I mean, I don't know. I would do that. Like, oh. I mean, for like a junior level like person, it's actually very impressive. So that's really the idea behind it. What are your questions?
Yeah, just for your example with the refactor code.
Yeah.
Is this figure that the space of the refactor code not constant compared to the one before refactor?
This should be linear.
This is linear.
This should be linear.
The other one is.
The other one is not, because I'm using an array and then I'm running dot includes as my lookup, which is not constant time. Right. So it's like linear plus, but like plus another iteration, which makes it. Yes, right. Like 2 iterations make it quadratic. Yeah.
Just curious, so we went through contours and a couple others. We got this. What about dot sort?
Dot sort is interesting in the way it's implemented. It will actually attempt to take in like the length of the array and figure out what the best thing is. There's so many ways to sort. There's like bubble, merge. I can't think of the other ones, but there's a lot. And if you look at the Ruby docs, it will actually attempt to run a certain function based on what you pass in. So it's hard to say.
Is there a way to know where it converges on the graph so that we can choose to have either quadratic, linear,
Okay, that's my fault in its explanation. Dang, I prematurely went here. Let me just scroll back up over here. Ba-la-la-la. You guys watch Big Hero 6? So the idea is that these are just terms in terms of understanding the scalability of speed. It doesn't necessarily mean that all your algorithms are going to be linear. It's going to be some sort of combination. So you'll have, in a more complex algorithm, you'll have like, oh, this is like, you'll have something like, the big O of this would be like O of n squared, like plus a log 2, like logarithmic time. And that whole thing is quadratic because I actually have to, everything is nested inside like a nested array. So if for whatever reason I needed to manipulate some data, this right here, like if this was my data structure, I would have an object, right? I'd have one key, constant time, another key, constant time. That's not affecting it. But then I'd have to go through everything in children, and then inside the data, I'd have something. And then if I wanted to look at the icon sizes, that'd be another nested iteration. So how can I pull the largest and smallest icon sizes of every object in this database? That would be like a question that you might, and it's not really a question, but that's sort of the idea that if you were to try to be able to explain it, like, great, I'm going inside an object, right? I have a quick lookup here, that's constant time, so that's sort of negligible. But then once I go through my first iteration, I know I'm at O of n. And then I have another constant time lookup of data, and then I have to go through another iteration, so I'm at quadratic time. But then if you have to do calculations, or this data is also like messed up, and you have to do something else to it, that might add a log, where you have to do some recursive function in here. So you will have quadratic and a log, and then you add them together. So then you'll say something like, oh, I have like a O of n squared plus like a log 2 of this other thing in order to get the data that I want. Does that make sense? That was like an example I throw on the fly. I thought it was okay. But yeah, you'll use the terminology, but you won't necessarily always say this is linear, unless it is O of n. All right, cool. That's all I have for you today.